Greetings 347 fans, and welcome to another video. This video is the second part of first order differential equations, which can be classified as linear. First order linear differential equations. In this video, we're going to be having a look at applications of first order linear differential equations. Okay, so the first application of first order linear differential equations is a familiar friend, which is Newton's law of heating and cooling. So I'll remind you that Newton's law of heating and cooling states that the rate of change of the temperature of a body is proportional to the difference between the temperature of the body and the temperature of the environment. So we had a look at this differential equation in our section on separable differential equations. In this section, we're going to have a look at this differential equation in the case where the temperature of the environment is Q of t, perhaps a function of time. You can imagine, for instance, that in a scenario where the heat goes out in your house, the ambient temperature might vary throughout the course of a day. So it turns out that Newton's law of heating and cooling applies to this case too, and all we have to do is replace our environmental temperature with the function Q of t. Now, as it turns out, the resulting differential equation, which again states that the rate of change of the temperature of a body is proportional to the difference between the temperature of a body and the environment, this new equation is no longer separable. On the other hand, this differential equation does turn out to be linear, and we can see that it's linear by rewriting it in our first order linear form. So to rewrite it in first order linear form, we multiply out the minus h on the right hand side of the differential equation and rearrange of form t prime plus ht equals h q of t. We can see that the integrating factor is e to the ht, and this allows us to use the integrating factor to view the differential equation as a product rule. Integrate both sides. Here we integrate using the dummy variable of integration s from s equals 0 to s equals t, and express the solution as a sum of an exponential term plus an integral in terms of h. So if we were given some sort of functional form for this ambient temperature Q, we could use this expression to come up with the temperature T. Okay, a second example of an application of a first order linear differential equation is the chemostat model. So I'll remind you of one of our variations from the chemostat model from our second video on separable differential equations, which is a chemostat model with variable flow rates, not equal flow rates, that is, Q in and Q out. So in that case, we saw that the volume in the chemostat is a function of time. That volume, of course, goes like V naught plus the net flow rate, V Q in minus Q out times time. In that case, we can transform that differential equation also to first order linear form, and we can do that just by using the product rule on this term VC all prime. So here we see that VC prime is the first times the derivative of the second plus the derivative of the first. So this term in parentheses Q in minus Q out is just the derivative of V times the second. So replacing this quantity VC all prime with V times C prime plus Q in minus Q out C on the left-hand side of the differential equation allows us to simplify and rewrite our differential equation in our first order linear form, and that form for the differential equation is C prime plus Qn over V times C equals Qn over V times Cn. Okay, so again, this is a first order linear form for the differential equation for which the integrating factor applies to solve it. I'll mention that other textbooks, instead of tracking the concentration, might track the amount or the mass or weight of the chemical instead, and you end up with a first order linear equation in that case too. This is also a good opportunity to point out that there's a typo in the textbook on this section on transforming the chemostat model using different flow rates in and out to a first order linear equation. So just compare what we had on that last slide to what you see in the textbook, and you'll see that they're a little bit different. The textbook has a typo in this particular case. Okay, a third application of first order linear equations is the application of sales. So this is a new application for us. In this case, we'll take S equals S of t to be sales per month. And in this model, we'll assume that sales change due to some sort of natural decay at a rate proportional to sales per month. And we'll see that sales change due to advertising increase. So you would imagine that if you advertise, that gives you an increase in sale that's jointly proportional to some advertising function A of t and to the relative untapped market with maximum M. Okay, so in this case, we'll assume that there's some sort of initial sales at the beginning of the month and derive a first order linear differential equation for sales together with that initial condition that'll form an initial value problem. So again, a few keywords here. The first keyword is a natural decay at a rate proportional to sales per month. Okay, so that should remind us of something we've seen before. And then here's a new keyword, jointly proportional. So jointly proportional means that the rate is equal to some constant times the product of those two items, namely the advertising function A and the relative untapped market. Now we've seen relative before also. Relative means that we're going to scale by that maximum. Okay, so in this case, here's what our model looks like. The rate at which sales change, S prime, is equal to R sub D plus R sub A, where R sub D is this natural decay, and R sub A is this advertising increase that's jointly proportional to some advertising function times this relative untapped market. So the term M minus S divided by M, if you think about M as the maximum sales in the market and S are the sales per month, then M minus S is the untapped market, the people whom you haven't sold to, divided by M gives you the relative untapped market. So here's the model. S prime equals negative KS plus R times A times M minus S over M. And it looks like here, instead of using the constant K in my first order linear form, I've replaced that with A for some unknown reason. So sorry about that inconsistency. It should be A above R sub D equals minus AS. In any case, if you rearrange that equation, you can see that our differential equation can be written in first order linear form. And here the first order linear form is S prime plus little a plus R times A over M all times S is equal to R times A. Okay, so again, the integrating factor applies to solve differential equations of this form as well, and you would have to make some assumptions in this model about an advertising function, and we'll see in our homework that that there's a rudimentary assumption made about advertising function, and we'll actually go ahead and solve the initial value problem using that advertising function. Okay, so the last application that we're going to have a look at is the application of a RCL circuit. For those of you of the electrical engineering variety, this example will be near and dear to your heart. A basic circuit components in an RCL circuit, there's some sort of source term, some sort of electric source. You can think of this as a battery that may be a function of time. The L in the RCL circuit stands for an inductor. The R in the RCL circuit stands for a resistor, and the C in the RCL circuit stands for a capacitor. And in this example, we'll derive a differential equation for Q, which is the charge in the circuit. In order to do that, we need to make some assumptions about how these different circuit elements act with respect to either current, which is change in charge, right? If you move charges, you get a current. So I, current, is Q prime. and relating those either currents or charges to the voltage. So the first one is a familiar one, Ohm's law. Ohm's law says that the voltage drop across a resistor is just equal to the resistance times the current through the resistor. V sub R equals R times I. The other two are similar assumptions about the voltage drop across a capacitor and the voltage drop across an inductor. So the voltage drop across a capacitor is 1 over C times the charge on the capacitor. And similarly, the voltage drop across an inductor is equal to the inductance L times the change in current I prime across that inductor. Okay, so these assumptions together with Kirchhoff's voltage law says that the total drop across the circuit elements is equal to the voltage supplied, or V sub L plus V sub R plus V sub C equals E of T, gives us actually a differential equation for Q, the change in charge. So in this differential equation, Q is the unknown function, and we can see here that this is actually a second order equation, which we'll again have a better look at next chapter, but for the time being we're going to go ahead and look at just RC circuits. So you can imagine that if there's no inductor in the circuit, you end up just with a first order equation for Q, and that differential equation is RQ prime plus 1 over CQ equals E of T, which again is the source term, or you can think of this as a battery. So as an example of an RC circuit, we'll assume that an aging battery generates voltage which decays exponentially, and that battery is connected in series with a 20 ohm resistor and a 0.01 farad capacitor, 1/100th farads capacitor. So you can think of the circuit diagram looking just like the one we had on the previous slide, except that there's no inductor. So we assume no charge at time 0. As you might imagine, that gives us an initial condition. And the goal here is to find the charge and also the current as time increases. And in this problem, we'll also identify the time at which the charge reaches a maximum. So the RC circuit equation, again, is R times Q prime plus 1 over CQ equals E of T. And again, in this case, we'll take the resistance R to be 20 ohms, the capacitance C to be 1/100th of a farad, and the source term E of T to be 200 times E to the minus 5t volts. So substituting those in, we can see that we have an initial value problem in first order linear form, which, when you divide both sides by 20, can be written as Q prime plus 5Q equals 10 times E to the minus 5t, where the initial condition is given by Q of 0 equals 0. Okay, so here we see that our integrating factor is going to be of the form e to the positive 5t. Multiplying both sides by the integrating factor, we see our product rule on the left-hand side, and it looks like I've got an extra factor of Q there. Sorry about that typo. That extra factor of Q shouldn't be there, but we can see that the left-hand side looks like the first times the derivative of the second plus the derivative of the first times the second, which reduces to e to the 5t times Q all prime equals 10, which can be integrated on both sides using a dummy variable s from 0 to 10, in which case on the left-hand side, we'll end up incorporating that initial value of 0. On the right-hand side, we'll end up just with 10 times t times e to the minus 5t once we account for the exponential on the left-hand side. So there's some simplification that's gone on behind the scenes here, so I encourage you to work through that on your own. For what it's worth, once we have the charge in the circuit, we can identify the current just by differentiating. So here are plots of the charge Q as well as the current I, and of course the charge is maximum Q when the current is 0, right? So this is just a calculus question. We can maximize Q by looking at zeros of its derivative, and in this case that happens when Q prime is equal to 0, or you can see from the right-hand side there of the equation for I. That happens at t equals 1/5 of a second. So of course, plugging in t equals 1/5 gives us this value for Q, which is just a little bit above 7/10. Okay, so examined a few different applications of first-order linear differential equations in this video, which we'll talk about more in class. Thanks for watching this video, and we'll see you again soon. So long for now.